presentation opportunity in this session. I am Jae-Nam Kim from Sungkyunkwan University and Samsung Electronics in South Korea. I will start my presentation with the topic a single-ended Duobinary-PAM4 transmitter with a 2-tap feed-forward equalizer. The sequence is as follows. First, I will tell you about the research background and motivation. Then, I will tell you about the proposed transmitter structure, measurement result, and conclusion. The data lace required by the interface continues to increase, and the negative effects of channel loss is also increasing. Currently, multi-level signalings are being actively studied to overcome the limitations of channels. In memory interfaces, multi-drop channels are used to increase the density. However, the multi-drop channels have a problem in that loss occurs severely. Therefore, we need a transmitter for the memory interfaces in multi-drop channel situations. And quarter-lake clocking is also being deeply studied as a way to reduce the dynamic power consumption of circuits. In conclusion, combining the above, we propose a multi-level transmitter for memory interfaces using quarter-lake clocking. As a related study, we will compare several signaling methods. The PAM4 signal has a disadvantage in that the SNR decreases because the eye height is smaller than that of NRG. However, when the two signals have the same data rate, the night-pitch frequency of PAM4 is half of the NRG, so it has the advantage of being less adversely affected by the channel. Next, a duobinary signaling is a signal generated by adding NRG, and NRG delayed by 1 unit interval. The duobinary has 3 voltage levels as shown in the eye diagram. It has the disadvantage that the SNR is smaller than that of NRG. But it has the advantage that the night-pitch frequency is 1.5 times smaller than that of NRG. In addition, the maximum transition magnitude of voltage levels in adjacent unit intervals is 1 step. That is, there is no transition from the lowest level to the highest level in adjacent unit intervals. As a multi-level signal after the duobinary and the PAM4, a PAM8 signal that transmits 3 bits per symbol and uses 8 voltage levels is being studied. A figure is an eye diagram simulation result of a 30 gigabit per second PAM8 signal. At this time, as the number of voltage levels increases, the eye sizes in the eye diagram of the signal become smaller. In particular, as indicated by the arrow, the eye sizes at the highest and lowest points become smaller, resulting in a bandwidth limit. This is because when the transition size of the data is maximum, the delay time is longest. Therefore, the eye widths at the highest and the lowest points are narrow. One of the advantages of our proposed Duobinary-PAM4 transmitter is that it can increase the eye widths and the highest and the lowest. Next, I will talk about the proposed Duobinary-PAM4 transmitter. In this page, we describe the existing method of creating Duobinary-PAM4 and the way we propose. If you use the existing duobinary making method as shown in the figure A, you can add the PAM4 and the 1 UI delayed PAM4_D to make the Duobinary-PAM4. The half-late clocks are needed to make signals like the PAM4 and the PAM4_D from the transmitter. The generated Duobinary-PAM4 signal has 7 DC voltage levels. We propose an encoding method for the figure B. The output is the same Duobinary-PAM4 as in figure A. However, the way to make it is to add PAM4 even and PAM4 odd signals. In the encoding method shown in figure B, only quarter-lake clocks are used in transmitters, which can reduce dynamic power consumption and facilitate design compared to using half-lake clocks in figure A. The upper right figures is an example of figure B. Since the MSB of the PAM4 signal is expressed as 2B and LSB as A, so the PAM4 signal is expressed as 2B plus A. The first advantage of the duobinary PAM4 is that the maximum transition size between adjacent unit intervals is limited to 3, regardless of input. Therefore, the duobinary PAM4 signal is relatively strong against crosstalk. The figure shows an eye diagram of signals. The duobinary PAM4 signal has 7 DC levels, and the blue fluorescent color, this one, represents the Nyquist frequency, which is the fastest frequency components of each signal. The table on the right compares eye height, SNR degradation, and Nyquist frequency under the same data range of all signals. At this time, if the Nyquist frequency of NRG is f_ny.nrg, the Nyquist frequency of PAM4 is 1 second multiplied by f, which is a half of NRG. And the Nyquist frequency of duobinary PAM4 is 1/3 multiplied by f by multiplying the Nyquist frequency of PAM4 by 1/1.5. As the Nyquist frequency is reduced, it has the advantage of being less affected by the harmful effects of channel loss. Also, the maximum transition in each signal is shown in red, the red one, shown in red. In the case of PAM8, the magnitude of the maximum transition level is from the lowest to the highest. However, since the maximum transition level of duobinary PAM4 is limited to 3 levels, like PAM4, the crosstalk effects and ISI can be mitigated compared to the case that allows full transitions from bottom to the top or vice versa. Also, assuming the same data range, the duobinary PAM4's Nyquist frequency is about the same as that of PAM8, which is 1.5 times less than that of PAM4. The table on the left shows each signal's SNR degradation according to eye height. The duobinary PAM4 has half eye height than the PAM4, so its SNR is about 6 dB less. Based on the previous observations, we can consider channel conditions that favor duobinary PAM4 signaling. For the duobinary PAM4 to be advantageous over the PAM4, the SNR increments obtained by overcoming the channel loss must be greater than 6 dB. An example of such a channel in memory interface is a multi-drop channel with a spectral hole in the channel loss graph. So we modeled the situation as shown in the lower right figure, and the graph in the upper right figure shows the insertion loss of a channel loss in the measurement setup to compare the PAM4 and the duobinary PAM4 signaling. The target data is 18 gigabit per second, and the channel has a notch at 4.5 GHz, corresponding to the Nyquist frequency of the PAM4 signal. At this time, the Nyquist frequency of the duobinary PAM4 is 3 GHz. In the upper right graph, the SNR increment by overcoming the channel loss is 8 dB, which is greater than 6 dB. Therefore, we can predict that the channel condition is in favor of duobinary PAM4 signaling. To confirm this experimentally, we check which signal survives after inputting duobinary PAM4 and PAM4 into this channel. Next, we will tell you the structure of the proposed transmitter. Figure illustrates the overall structure of the proposed dual mode transmitter. The 64-bit data generated by on-chip PRBS generator is input to the 60 to 8 serializer, and the 8-bit 2.25 gigabit per second parallel data output from the serializer is input to the encoder. The brake driver includes 2 functions. First, it can choose between the PAM4 output mode and the duobinary PAM4 output mode. Blocks that generate 2 signals are included, and only the signal to be output is selected and output from the driver. The second feature is the two-tap feedforward equalizer. Therefore, it generates main and post signals and can set the tap coefficient to 8 to 0, 7 to 1, or 6 to 2. The 8.5 GHz clock is provided by an external clock source routed to the data path after passing through the duty cycle corrector. Next, we will give a detailed explanation of the predriver. In a retimer in predriver, the signals to make the Duobinary-PAM4 data and the signals to make the PAM4 data are aligned according to the appropriate clock. The current page shows the case of the Duobinary-PAM4 data and main signals. The MSB and LSB signals go through the flip-flop, and the even signals are aligned using C2Q, which is corollary clock, and the odd signals are aligned using the C2IV clock signal. The current page shows the case for PAM4 data. In order for both signals to have the same data rate, the data pattern in the PAM4 mode must be twice as fast as in the Duobinary-PAM4 mode. Therefore, a 2-to-1 mux is additionally used in the encoder for the PAM4 mode. This table shows the output signals of the retimer in the predriver. The difference between the Duobinary-PAM4 signal and the PAM4 signal in retimer is that the period of the PAM4 signals is shorter. Therefore, this is why there is one more 2-to-1 mux in the PAM4 signals retimers. All signals with the names listed here to go directly to the input of the mode selector. In the predriver, the outputs of the retimer are routed to the input of the mode selector. And in mode selector, when the dual_en signal is turned on, the Duobinary-PAM4 signals are delivered to the mux output. When the dual_en signal is turned off, the PAM4 signals are delivered to the mux output. There are 16 mux in the mode selector, which can be grouped into 4 groups as indicated by the square boxes in the figure. The green box in the front transmit the Duobinary-PAM4 MSB even signals, and the green block in the middle sends the Duobinary-PAM4 MSB odd signals. We will tell you about the 2-to-1 mux block in the predriver. In the 2-to-1 mux, the data is serialized by selecting an appropriate clock for 2 types of data having different data speed patterns depending on the signaling mode. Therefore, we designed the mux to select the required clock depending on the mode. On the current page, you can see in the figure on the left that C2Q and C2QB, which are corollary clock, are used for Duobinary-PAM4 data. A half-rate clock, C1, is used for PAM4 signal, and a correlate multi-phase clock is used for the Duobinary-PAM4 signal. Next, we will explain on equalization control block. The EQ control block can adjust the tap coefficient of FFE. The EQ control block consists of 4 bundles as shown in the figure on the left, and each bundle contains 3 mux. The main signal or post signal, which is the output of the 2-to-1 mux block, is input to this mux. As shown in the upper right table, if both EQ_en signals are low, then only the main signal is sent to the driver. And according to the EQ_en signals, the post signal with the tap coefficient change is transmitted to the driver. 6 driver segments are connected to the mux that transmit only the main signal. 1 driver segment is connected to each of the 2 mux below that transmit the post signal. Therefore, we can choose the ratio main to post equals 8 to 0, 7 to 1, or 6 to 2 for the main and post data, which means 0 dB, minus 2.5 dB, and minus 6 dB. Next, I'll explain about the driver and duty cycle corrector. Figure shows the structure of the voltage mode driver. The driver is partitioned into 300 ohms, 6 blocks marked with a yellow box to make 7 voltage levels in the Duobinary-PAM4 mode. Each driver block consists of 8 segments for FFE operation. And to adjust the tap coefficient of the FFE, 6 out of 8 are always used for main data, and the other 2 are used for main data or post data, depending on the tap coefficient. The impedance of single driver segment is calibrated to 2400 ohm, so that the total impedance of 48 segments is matched to 50 ohm. Therefore, it is possible to adjust the tap coefficient of the FFE while maintaining the 50 ohm matching condition. In the case of PAM4 mode, 2 blocks operate 1 block to generate 4 voltage levels. By using a programmable resistor, the resistance change of the driver according to the corner and temperature is corrected. The 4.5 GHz operating clock is provided on external clock source routed to the data path after passing through the duty cycle corrector. The DCC is carefully designed because the output signal quality heavily depends on the duty cycle accuracy of the driving clock. Figure shows the structure of DCC. The DCC operates through negative feedback between the offset calibrated differential amplifier and the current start inverters. A duty cycle error of C1 is output to VP DCC or VNDCC through a low-pass filter and amplifier. VP DCC and VNDCC adjust the duty by changing a pull-up or pull-down strength of the current start inverters. Next, we will present the measurement result and performance summary. Figure on the left shows eye diagrams of transmitter measured after turning on the TX equalizer in PAM4 mode and Duobinary-PAM4 mode at 18 gigabit per second in a 28 nanometer CMOS process. We use 1.1 volts as the I/O supply voltage, and the peaking gain of the equalizer is 2.5 dB. As the result, the eyes of both the Duobinary-PAM4 signal in figure A and the PAM4 signal in figure D are opened before passing through the channel. However, after passing through the channel, it is confirmed that the eyes of the Duobinary-PAM4 signal are opened in figure C, and the eyes of the PAM4 signal are closed in figure F. This is because the PAM4 signal is more noticeably affected by attenuation than the Duobinary-PAM4 signal. The amount of increase in SNR obtained by Duobinary-PAM4 signal overcoming the channel loss compared to the PAM4 signal is 8 dB. This increase is greater than 6 dB reduction in SNR caused by the smaller eye size. Therefore, in the channel used for measurement, the Duobinary-PAM4 signal dominates when the data rate is 18 gigabit per second. The picture is of a chip tape-out with Samsung's 28 nanometer low power bulk CMOS process. There are 26 paths in total, and different paths are used depending on the purpose of VDD, VSS, analog voltage, high-speed I/O, and etc. Also, the parasitic capacitance of each path is about 400 picofarad, and the wire bonding inductance is about 1 nanohenry. Table on the right shows power breakdown summary. In the Duobinary-PAM4 mode with the quarter ray clock, the energy efficiency is improved by approximately 33% compared with that of the PAM4 mode with the half-ray clock. The table is a performance summary table of the design transmitter. Because the memory interface is target, a single-ended is chosen, and the driver topology is the SSD. At 18 gigabit per second, the proposed transmitter achieves 1.11 picojoule per bit and 1.66 picojoule per bit energy efficiency in Duobinary-PAM4 and PAM4 modes respectively. Finally, let us draw our conclusion. The PAM4/Duobinary-PAM4 dual mode transmitter with 2-tap FFE for memory interfaces is demonstrated in 28 nanometer CMOS. In this regard, the Duobinary-PAM4 signal can be advantageous in multi-drop channels over the PAM4 signal. And to reduce the dynamic power consumption of transmitters, we designed the low power transmitter by encoding the signal with correlate clocks. The proposed transmitter includes 48 XST driver segments divided into 6 blocks to generate the Duobinary-PAM4 signal and apply the 2-tap FFE. As a result of the measurement, at 18 gigabit per second, the proposed transmitter achieves 1.11 picojoules per bit and 1.66 picojoules per bit energy efficiency in Duobinary-PAM4 and PAM4 mode respectively. I thank you for your attention and I'm ready to take your questions.
Thank you for your presentation. The session now is for questions. Does any on-site audience has any questions or online? No. Okay. I have a question. We can see that the PAM4 mode, the dual-PAM4 mode, Duobinary-PAM4 mode in your design performs better eye diagrams better than the PAM4, right?
Yeah.
But I think it is specific for the channel. We can see that has a not very smooth response since there is a dip in the 4.5 gigahertz, right?
Yeah.
So if the channel now we has a more smooth response, the technique in your design can present the better results.
Yeah.
Can come in.
So, do you mean if I use the smooth channel, not like this channel, then it means the PAM4 signal is gonna be better than the Duobinary-PAM4 signal, right?
Yeah.
Oh, yeah, that's right. But in the field of multi-drop channels, this kind of spectral hole is always founded because of the notch or reflection. Yeah, because if there is notch in the pad or in the how can I say, in the
So
channel,
I mean
then, yeah.
the frequency response, the dip is result from the multi-drop application, right?
Yeah.
But the reflection makes the dip frequency may be various for different channels. So maybe in other channel, the frequency is not on the 4.5 gigahertz, and the PAM4 may be not degrade so much, right?
So the point is we have set the 4.5 gigahertz to the PAM4's Nyquist frequency to show that the Duobinary-PAM4's Nyquist frequency is 1.5 less than the PAM4 frequency, and also it has the power that it avoids the limitations of this spectral hole from the multi-level from the multi-drop channels. So we set this spectral notch to the PAM4's Nyquist frequency on purpose.
Okay.
Yeah.
Any questions? I have one more question. I see that in your architecture you have a duty cycle correction, but in your Duobinary-PAM4 application it's a quarter rate clocking. So do you have any quadrature phase calibration?
Actually, in this structure, duty cycle corrector and the quarter and the QEC are also needed, but our setting, in the measurement setting, the DCC, the duty cycle collectors operation was more effective than the QEC. So we only put DCC instead of the QEC. But as you mentioned, if we get the more specific and more detailed duty cycle and also quarter duty cycle, then the QEC also needed after the DCC. But about the measurement setting, we only put the DCC because it calibrates. It calibrates of the duty increase to the both clock and clock B, or duty decrease to the both clock and clock B.
Okay, thank you. So if you learn now